Hello. Here is the video going over graphing rational functions. So the first thing we're going to do is factor our rational function to see it in factored form, because factored form is the form that's going to give us the most information. So in my numerator, I do have this number in front of my x squared. So I'm going to start by multiplying my first and my last. That gives me negative 12. And two numbers that multiply to negative 12 and add to 11 are positive 12 and negative 1. So I'm going to write this as x plus 12, x minus 1, and of course, since we started by multiplying by 2, I need to divide both of those by 2 to get my factored form. So one factor is going to be x plus 6, because that 12 over 2 reduces. And then my second factor, since my fraction is already reduced, this denominator just becomes the coefficient of your x. So my second factor is 2x minus 1. For my denominator, two numbers that multiply to negative 42 and add to negative 1 are positive 7 and, negative 7 and positive 6. So I notice right away after I have factored it that I do have some factors that are the same on top that's the same on the bottom. So I can go ahead and cancel these two factors out. So my leftover function is 2x minus 1 over x minus 7. Now, all of the different characteristics that we are going to list come from specific things within our factored form. So our domain comes from the denominators, because you can never divide by 0. So you are going to list all the values that x cannot be from the denominator. So for x minus 7, x cannot be 7. And for x plus 6, x cannot be negative 6. Now, even though we canceled it out, it still creates a restriction on our domain. So our two values of x that our function cannot have are 7 and negative 6. Your zeros will come from your numerator. So they are factors of your numerator. So they come from zeros of the factors of your numerator. So my numerator has this 2x minus 1. So the zero of that factor would be positive 1/2. So my zero, or x-intercept, because it means the same thing, is going to be positive 1/2, comma 0. Your y-intercept comes from plugging in 0 into your function. So my x-coordinate is 0, and then for my y-coordinate, I'm going to go ahead and plug it in. You can plug it into the original or the leftover. It should not matter, but that gives me positive 1/7. Since I end up with negative 1 over negative 7, that becomes a positive 1/7. Your wholes come from your canceled factors. So whatever cancel factors out, or whatever, said that wrong, whatever factor cancels out, that is going to create a hole in your graph. So the x-coordinate of your hole comes from the 0 of the canceled factor. So the canceled factor was x plus 6, so the 0 of that is going to be negative 6. And to find the y-coordinate of that hole, that is going to be when you plug in the x-coordinate into your leftover. So I have 2 times negative 6 minus 1 over negative 6 minus 7. That gives me negative 12 minus 1, negative 13 over negative 13, which is positive 1. So we have a hole at 6, comma 1. Your VASI, or your vertical asymptote, comes from the denominator. So if I look at my leftover function, that denominator is an x minus 7. So that means I am going to have a vertical asymptote at x equals 7. Now, one thing I do want you to notice is if we look at our restricted domain, 7 and negative 6, both of those coincide with what we have for our hole and our vertical asymptote. So anytime we have values that are restricted from our domain, they are either going to create a hole or a vertical asymptote. Your HASI, or your horizontal asymptote, comes from comparing your degrees of your original function. So if I look at my degree, your degree is your highest exponents. So my highest exponent in my numerator is 2, so my degree is 2 in my numerator. And in my denominator, my degree is also 2. When your degrees are the same, your horizontal asymptote is going to take the form of y equals a over b. Well, what is a over b? A and b are your coefficients of your numerator and your denominator. So my coefficient of my numerator is 1 or 2, and the coefficient of my denominator is 1. So that means my horizontal asymptote is 2 over 1, or just y equals 2. Okay. There are other scenarios, like if your degree on top is smaller, then your horizontal asymptote would be y equals 0. And if your degree on top is bigger, then you actually don't have a HASI. You end up having a slant asymptote, which I think you'll see with the next problem. Okay, so let's go ahead and start graphing. I'm going to start by graphing my vertical asymptote at 7. That is going to be a vertical dotted line through x equals 7. And my horizontal asymptote is at y equals 2. So I'm going to go ahead and cross my y-axis at 2. And your asymptotes are lines that your graph is going to approach. They may not touch them, they may not cross them, but they are going to approach them, so it kind of guides us as to what our curves are going to look like. For our points, I have an x-intercept at 1/2, 0, so that's right here. I have a y-intercept at 0, 1/7. About right there. It's kind of hard to graph these small numbers because your grids are so close to each other, but just try your best. And I have a hole at -6, 1. So -6, 1, I'm going to go ahead and draw the hole. Now I can kind of see my graph taking shape. So if I were to connect all of these points together, I can see that it's going to taper off in this direction. So I'm just heading towards that asymptote in both directions. Now, rational functions typically go in opposite directions when you hit a vertical asymptote. So that means the other piece of my graph is going to look something like this. And it's going to taper off towards this end on the right-hand side. It's going to keep going in this direction, tapering off towards this horizontal asymptote. Okay. The other piece that you are going to be asked about is your end behavior. So if I look at my graph, your end behavior is what is happening when x starts to get very, very large towards positive infinity or towards negative infinity. And I can see that both pieces of my graph are approaching that horizontal asymptote. And my value for my horizontal asymptote is 2. So in both directions, your function is heading towards that horizontal asymptote of 2. So this end behavior corresponds to your horizontal asymptote, or your HASI, like we will call it in class. So there is your first graph. Your second graph, I'm going to go ahead and start by factoring it. So two numbers that multiply to -28 and add to -3 are -7 and +4. And in my denominator, I just have x minus 3. So nothing's going to cancel this time around, which means we're not going to have any holes. So I'm going to go ahead and jump down there and write that we aren't going to have any holes. My domain restriction, x cannot be 3. And your zeros come from your numerator. So my first factor in my numerator is x minus 7. So that means I'm going to have a 0 at 7, 0. And I'm also going to have a 0 at -4, 0, because it comes from my numerator. For my y-intercept, I'm going to plug in 0. So I have 0 minus 7 times 0 plus 4 over 0 minus 3. So that gives me -28 over -3, so positive 28 thirds. All right. Vertical asymptote comes from your denominator, so I'm going to have a vertical asymptote at x equals positive 3. And for my horizontal asymptote, we're going to compare the degrees. So highest exponent on top is 2, so my degree is 2. And on the bottom, your highest exponent is 1, so my degree is 1. So I can see that my degree on top is bigger than the degree on the bottom. So that means you actually do not have a horizontal asymptote. You have a slant asymptote, which is what is listed over here on the right-hand side. Now, for these particular notes, you do not actually have to find the slant asymptote. We will save that for a different lesson. But your slant asymptote is this diagonal line on your graph that is already set up for you. So it's this this diagonal line, y equals x. I can also graph my vertical asymptote at x equals 3. So I'm going to go through 3 on my x-axis. And I have this vertical dotted line as well. And let's go ahead and start to plot our points. So we have a 0 or x-intercept at 7, 0. So that's this point over here. We also have one at negative 4, 0. So over here. And we have a hole at 0 and 28 thirds. 28 thirds is the same thing as 9 and 1/3. So that's going to help me graph it. So 0 and a little over 9. I'm going to go ahead and graph the hole right there. Now, as I connect these points, again, I want to taper towards the asymptote. So I can go ahead and connect these 2 points over here, and I can continue towards the asymptote in both directions. And again, your rational functions will usually go in opposite directions at your vertical asymptote. So I can go ahead and do the other side through this other 0 and head in the opposite direction along my asymptotes. Okay, now with the last example, our end behavior corresponded to our horizontal asymptote. This time we do need to actually look at our ends. So I'm going to look over here. So as x goes to infinity, this portion of my graph is going to go towards positive infinity. And as x goes towards negative infinity, this portion of the graph is going to keep going down towards negative infinity. So for my end behavior, I have positive infinity as the graph continues to the right, and negative infinity as my graph continues towards the left. All right, last graph. So once again, let's go ahead and start by factoring. Numerator cannot be factored any further, so we'll leave it alone. In the denominator, 2 numbers that multiply to 36 and add to negative 12 are x minus 6 with another x minus 6. We can always condense this further to write it as x minus 6 squared. Okay, so for my domain, since my factors are the same, we really only have that one restriction of x cannot be 6. For the zeros, that's coming from my numerator, so I'm going to have an x-intercept at negative 4, 0. And for my y-intercept, I'm going to plug in 0. So I have 0 plus 4 over 0 minus 6 squared. That gives me 4 over 36, which reduces to 1/9. I did not have any factors that canceled, so I do not have any holes. And my vertical asymptote will come from those factors of x minus 6. Now, I do want you to notice that those factors are used twice. So that's going to create a shift in what happens at that vertical asymptote. So my vertical asymptote is x equals 6, and we'll talk about what's happening there as we continue to sketch the graph. And for the horizontal asymptote, I'm going to compare my degrees. Degree on top is 1. Degree on the bottom is 2. So this time I have the scenario where my degree on top is smaller than the degree on the bottom. So that horizontal asymptote is going to be y equals 0. So if you recall from our first example, our degrees were the same. So that told us our horizontal asymptote was going to be in the form of y equals a over b. For the second scenario, our degree on top was bigger, so you did not have a horizontal asymptote. And for our third scenario, our degree on top was smaller, which means our horizontal asymptote is going to be y equals 0. Okay, let's go ahead and start graphing things. My horizontal asymptote of y equals 0 is the x-axis. And I have a vertical asymptote at x equals 6. So there's this other piece of my graph. And I'm going to go ahead and plot some points. So I have an x-intercept at -4, 0. So it's right here. And y-intercept at 0, 1/9. So about right there. And that's pretty much all the information that I have. So as I continue to graph this, I do want to plot my points in a logical way. So I can see it when I connect these 2 points. My graph is going to start to increase as I move to the right. So I'm going to head up towards this asymptote, and then it's just going to continue to the left. Now, here's one important thing about this vertical asymptote, since it came from your denominator that was squared. So since this denominator was squared, I want you to think about your multiplicity that we did with polynomials and how when you had an even multiplicity, it would bounce at that particular 0. So at this particular vertical asymptote, it's actually going to be going in the same direction on the other side. So this graph ends up going in the same direction at that vertical asymptote as opposed to the other 2 graphs which did not. So when I look back at my other 2 graphs, at my vertical asymptote, they were going in opposite directions for this one as well. But because this vertical asymptote came from a squared factor, your ends are going to end up going in the same direction at that vertical asymptote. Now, for your end behavior, I can see that my graph is heading towards the horizontal asymptote in both directions. So my end behavior is going to be 0 as my graph moves to the right and 0 as my graph continues to the left. All right, so that concludes our video on graphing rational functions.